Cold fusion is a broad term for a type of controlled nuclear fusion that can be induced and sustained at room temperature. It's called cold fusion because normal room temperature, or somewhere thereabouts, is quite cold compared to the environment in which fusion reactions typically take place. The pressure and heat are often quite extreme, as both are generally required to force elements that typically would not combine to combine, which is the fusion part of cold fusion. And that combination of elements is what creates energy. Early research in this space actually began back in the 1920s, when a couple of Austrian scientists seemed to have witnessed hydrogen converting into helium, so the element with an atomic number of 1 changing into the element with an atomic number of 2, implying that the process they were experimenting with, which involved dividing pieces of palladium into tiny bits, in turn causing those bits to absorb hydrogen, actually caused that hydrogen to combine into helium. Which, well, that would have been amazing, except that that's not what happened. Those scientists later retracted their report, indicating that the helium they had detected was actually naturally occurring helium from the air that they had interpreted as being otherwise, as being the consequence of this thing that they were doing. Several other fairly big-name researchers and institutions invested their time and resources in this field soon after, attempting various approaches to see if they could combine elements in this way to create a new element, but also, and this was the real goal for most of these projects, to create energy as a byproduct of that combination process. Because that energy creation, the same type that takes place in stars, including our sun, by the way, if we can make that happen at something closer to room temperature rather than star temperature, we might be able to create abundant, clean energy with few or even zero harmful byproducts. Despite that potentially society-shifting reward, however, the field of cold fusion remained fairly obscure for decades. The term was coined sometime in the mid-1950s. The New York Times published a piece containing the phrase cold fusion in 1956 to refer to Luis Alvarez's then contemporary work on something called muon-catalyzed fusion, an approach to traditional fusion methods that allowed the temperatures involved to be significantly lower than with typical unaugmented fusion, because some of the electrons involved were swapped out with muons, which are denser, about 207 times more massive than electrons, which means that if you swap one in for an electron, in a hydrogen molecule, the nuclei pull in about 196 times closer to the center than in a normal molecule, which in turn dramatically increases the chance that nuclear fusion will occur. So that method that was being written about in that Times piece made it more likely that fusion would occur at something closer to room temperature, but it wasn't what we normally think of when we think of cold fusion today. It was not as controlled, and it wasn't consistent and predictable enough to use as a source of power. It was more like a proof of concept, at least at the time. This field and this term really took off, though, in the late 1980s, when two scientists, Stanley Pons and Martin Fleischmann, of the University of Utah and the University of Southampton, respectively, announced that they'd managed to produce excess energy, essentially create more energy than they invested in a room temperature fusion project, which involved using palladium and heavy water, which is water made with deuterium, which is a fairly common naturally occurring stable isotope of hydrogen. That means that it is like hydrogen, but instead of one proton and one electron orbiting it, it's got a proton and a neutron in the center, and that same electron in its orbit. So these scientists took that heavy water, that water made with more than the normal amount of deuterium, which gives the water somewhat different properties because of its increased mass, and they put a cathode of palladium, a rod made of palladium with a negative charge, and stuck both in what's called a calorimeter, which is an insulated container that measures heat. Current was then applied, a positive charge that entered the vessel via an anode, which is the opposite of a cathode. Both carry opposite electrical charges. And the heavy water was thus electrolyzed, was exposed to electrical energy that could catalyze a chemical reaction for several days, with the heavy water being topped up at regular intervals. Fleischmann and Pons discovered that during this process, the amount of heat being emitted would sometimes spike to higher levels than was expected. The expected heat, based on the energy being pumped into this vessel, was about 30 degrees Celsius, or about 86 degrees Fahrenheit. But in some of their experiments, the temperature would increase to around 50 degrees Celsius, or 122 degrees Fahrenheit, without any increase to the amount of energy being invested. In short, it seemed like they were, for brief periods of time at least, able to put in a little energy and get more than that little bit of energy out. They were able to, maybe, create a useful fusion reaction at room temperature, that which time could be better understood and harnessed, producing more and more clean energy as they scaled up the amount that they invested. They applied for funding from the U.S. Department of Energy back in 1988, and in 1989 they published their work, reportedly stabbing a colleague in the back as they did so. A scientist named Stephen Jones from Brigham Young University, who they'd spoken with previously, who was working on things from a different angle, and who had, according to his version of the tale at least, agreed to wait on publishing his work so that they could all publish on the same day. These two got the jump on him, though, and he, feeling betrayed, published the next day, getting far less attention for his work as a consequence. Whatever the truth of that supposed backstabbing, Fleischmann and Pons got their names on this method and this potentially history-making discovery. It's perhaps just as well for Jones that he's less remembered for his work at this moment, however, as their fame and good names were not going to last for long. Immediately after that publication and a press release announcing it, though, Fleischmann and Pons were legitimately famous, garnering a great deal of media attention, numerous interviews and speaking gigs, and their paper could not have arrived at a better time to receive a positive reception. A few years before, high-temperature superconductivity, the discovery of materials that, when heated up, conduct electricity with far less resistance, opening up all kinds of technological and electrochemical possibilities, but also defying what we understood until that moment about conductivity and crystalline structures and numerous other things involved in the discovery. That had just blown the collective minds of the scientific community, perhaps making everyone a little bit more receptive to discoveries that didn't yet fit within the comfy confines of existing scientific knowledge. This was also not long after the 1973 oil crisis, the beginning of public rumblings about global climate change, which at the time was still generally called global warming, and there was a big push to shift away from nuclear power for reasons ranging from the 3 Mile Island and Chernobyl nuclear incidents to the overlap of nuclear power and nuclear weapons, a distinction that few people made at that point in history. These were also scientists with impressive credentials and imposing institutions backing them, being reported upon by an enthusiastic press that, at times, acted as stenographers for the claims being made by these immensely credible scientific authorities. Within the year, though, that celebration train came to a complete halt, as scientists at institutions around the world were unable to replicate the discovery. And when they did manage to get something similar, it was thought and then shown to be the consequence of sloppy work, of contamination of the experiment by other substances, which, when added to the reaction, explained away the temperature spikes without requiring cold fusion. Fleischmann and Pons tried to wrangle the conversation later that year with a note in a scientific journal and a plea to get funding from then-President Bush Sr., but the concept was declared dead by the New York Times at the end of April 1989, and a slew of other former enthusiasts did the same in the following weeks. Fleischmann and Pons had their meetings with higher-ups in the government canceled, their talks were pulled from conferences, and their findings were declared inconclusive and not worthy of investment by the U.S. Department of Energy. The Fleischmann and Pons debacle was called pathological science by a physicist representing CERN at an American Physical Society session on cold fusion. Pathological science being research where results seem more convincing than they are, and in which generally skeptical people are emotionally dragged into increased gullibility due to wishful thinking. He basically said that they were so excited about the possibilities of it being true that they dismissed what their critical brains were telling them, and by the time their work had made them famous, it was far too late for their reputations and their internal senses of self and credibility to pull back and question what they were saying, to question how it was done and what could have gone wrong. to even ask themselves whether they could have been wrong. The National Cold Fusion Institute was founded and funded by the state of Utah in late 1989, despite all the negative hubbub, but it ran out of money and, to some degree, interested parties 2 years later in 1991. It closed that year, and around that same time both Fleischmann and Pons left the world of academic research to take jobs in the public sector, doing some work related to cold fusion here and there, but nothing publicly notable, and both mostly remained off the public radar ever since that massive and public fall from grace. What I'd like to talk about today is cold fusion, why it's considered to be such a fool's errand by so many people within the scientific establishment today, and what we've been learning from recent investments and efforts in this space. You're listening to Let's Know Things. I'm Colin Wright. If you're enjoying Let's Know Things, please consider helping to spread the word by leaving a quick review up on Apple Podcasts or wherever you get your podcasts, or by sharing the show with a friend who you think might enjoy it, or sharing your favorite episode with your social network of choice. Those reviews are particularly important. There are, as of the moment I'm recording this, at least 389 reviews on the US Apple Podcasts platform. Now, these numbers are not inherently meaningful, but they are in the sense that they add a certain amount of credibility to the show for folks who are considering listening but do not yet know whether or not this is a serious thing that they should commit their time to. And that's understandable, that this is an indie show not produced by a big podcasting conglomerate or some other existing entity of that kind, and that it's kind of an other sort of genre. It is a genre-straddling show that is also somewhere in the neighborhood, usually, of 30 to 60 minutes. So it's a big investment of time, especially if you are coming to it blind and don't know what to expect. So if you have a moment and if you are enjoying the show, it would be absolutely wonderful and very helpful to anybody who might enjoy it, but who is not yet certain if they should give it the time and listen to it yet, if you would leave a quick review. Up on Apple Podcasts in particular, that is the biggest source of podcasts in the world and the most prominent source of reviews that other apps use as well. But wherever you get your podcasts is also important and appreciated. Thank you very much to everyone who's already taken the time to do so, those 389 and more in other countries and counting, and thank you in advance if you are considering doing so in the future. All right, let's get back to the show. In the years since Fleischmann and Pons, cold fusion has become a bit of a pop cultural trope, a stand-in for science that would solve everything, that would save the world, that by implication would make everything better pretty much immediately, forever and ever, amen. This isn't really the case, of course. Even if the aforementioned, unfortunately overhyped 80s and 90s era discovery had turned out to be the real thing, chances are good that making fusion at room temperature sustainable, practical, and cost-effective would still be a fairly steep hill to climb. There's a chance that if we had invested heavily in it, and it had worked, we would have a lot of clean power plants and other use cases for this technology by now, but maybe not. There are so many unknowns with this kind of thing that it's often more fun to think about in fiction than in reality because of those uncomfortable, gritty variables that keep anything from being the be-all, end-all pretty much ever. Now that said, this technology did seem very inevitable for a moment there. And because of that, and the fact that there is somewhat convincing evidence-like material and scientific writing that exists that seems to indicate that it is a real thing, rather than a thing that seemed like a real thing before it was shown not to be a real thing, there is a conspiracy theory that still abounds, still has space amongst all the other incredibly popular conspiracy theories of today, that says, we have cold fusion, we made it work, but for one of several reasons it is being held back, kept from us regular folks because the higher-ups are using it for themselves, because it would put the oil and gas and coal industries out of business, or because it's part of a timeline-driven plan to slowly introduce alien technologies to humanity in a way that keeps us from officially finding out that we've been contacted by those aliens, until we are in a peaceful enough state to deal with that reality like mature adults, rather than nuke-launching children, which is apparently where we are now. This conspiracy theory exists alongside other similar theories about a variety of no-cost pollution-free technologies that supposedly exist, but which are being kept from us for all kinds of colorful reasons. But just like the theorized perpetual motion machines, the torus-based generators, and quantum vacuum zero-point energy, any of which could potentially, maybe someday, be actual energy sources, but none of which are, according to currently understood science, cold fusion remains a work of fiction and fantasy, despite what some cold fusion truthers on YouTube might claim. It doesn't help that some of the proponents of these and other theories and areas of research related to things like cold fusion have at times died of things other than old age. One of them, a guy named Eugene Malov, was actually murdered, though they caught the people responsible, and it turns out it was related to Malov evicting one of the murderer's parents from his childhood home, which was a rental property until it was forcibly vacated by him. Another of them, a guy named Stanley Meyer, who claimed he created what he called a water fuel cell, which purportedly powered a car using electrolysis on water in a container before combusting the resultant gases to move the car, which, by the way, is something that is sort of feasible, but not without spending more energy to break apart the water than you create as a consequence, and definitely not in the way that he claimed. Meyer was found to be a fraudster by an Ohio court and was forced to repay investors the money that he swindled from them, because he knew the whole time that the tech he was pretending to use in the little dune buggies that he drove around town was not real. Later in life, in 1998, he died of an aneurysm while eating out at a restaurant, and while it was happening, he got up and ran outside shouting, "They poisoned me," which certainly helped fuel the resultant conspiracy theory flames, despite there being no evidence of poison in his system or reason beyond pure speculation to assume that he was poisoned in a way that apparently caused an aneurysm, which is something for which we do have medical evidence. Regardless of this particular continent in the world of conspiracy theories, though, there are some interesting what-if avenues to be taken here if we're thinking about how the world could have changed had Fleischmann and Pons been right. And I should note, it's generally thought that they were not intentionally scamming anyone. Unlike Meyer and some of the other hucksters that have invaded this space in the past few decades, these guys legitimately seemed to believe in their research despite having it shown to be unsupportable later. But it's an interesting thought, isn't it? What might the world look like if we had something like this, a technology that would theoretically, at scale, if we set it up right, allow us to generate essentially endless clean energy to the point where it might even be free, or at the very least insanely cheap? How would that change things? Economics, international diplomacy, environmental worries, so many of these things which are core to so many other things that we worry over, that delineate the destinies of societies and individuals, trace back to energy-related concerns, if you follow their thread far enough. And those concerns could be changed radically, presumably for the better, as a consequence of this type of technology being introduced. There are 2 articles that I'd like to start with today. The first comes from the blog of the science journal Nature, and it's entitled, "A Google Program Failed to Detect Cold Fusion, but is Still a Success." And the second is from the Futurism blog, and it's entitled, "Google's $10 million Cold Fusion Project Has Failed." That first piece, from Nature, relates the findings of a recent research paper that they published, entitled, "Revisiting the Cold Case of Cold Fusion," and this piece is at the center of both articles. And I picked these 2 to unspool, despite there having been so many pieces on this story to choose from, because they take the same information and present it from 2 completely different angles. Nature has declared that this research project failed to make cold fusion work, and as a result is a success. Futurism has declared that they failed to make cold fusion work, and as a result, the project is a failure. Let's talk first about the research project in question. In 2015, Google funded a group of about 30 researchers working in several different laboratories and tasked them with looking into the previously posited, theorized potential mechanisms of achieving cold fusion via what are sometimes called benchtop methods, meaning methods that do not require large-scale and fantastically expensive machinery. The bench, in this case, is the workbench in a lab, so they were tasked with working through a trio of lab-based, relatively inexpensive methods of potentially achieving cold fusion that had been previously posited but which had been only casually or irregularly tested. Those 3 previously performed experiments were replicated under the strictest of conditions, tested with sufficient rigor to say for certain whether or not they pointed toward a legitimate path of further exploration. This was an exercise, then, less in novelty and more in reproducibility and concreteness. Those involved didn't necessarily think any of these methods would work, but they wanted to check them off the list just in case, because there was a chance, even if just a small one, that one or more of these experiments could have been wrongly cast aside decades ago, leaving us with a workable, scalable method that was ignored because of the reputational damage that often comes with serious research into cold fusion, post-Fleischmann-Pons, and the very public fallout of their much vaunted but ultimately mistaken work. This lack of positive outcome, and the sense that we didn't end up with a way of inducing practical cold fusion, is what led to that headline from Futurism. By their assessment, the declaration by those involved in the dozen or so papers these researchers have published over the last 4-ish years on the subject, and the final overarching piece that was published in Nature about the totality of the projects within that larger project, that there was, quote, no evidence whatsoever, end quote, of actual cold fusion happening with any of these methods, truly sucks and makes that $10 million or so that Google invested in this research seem like money badly spent. The counterpoint to that thinking, though, as written in that piece on Nature's blog, is that this experiment put to rest in a very conclusive, well-documented, replicable, rigorous way some of the most commonly wondered about approaches that we kinda sorta knew wouldn't work, but also had a little bit of hesitancy about declaring fully dead in the water. In other words, we can now say with the greatest possible surety that these methods won't work and can adjust our worldview and our future research dollars accordingly. And that, by their estimation, is money very well spent. In addition to that greater level of certainty, there were also multiple spin-off innovations from the time and money invested in this project, including a new type of calorimeter that operates reliably under extreme conditions, and a system that allows us to more accurately and reliably produce and categorize highly hybridized metals. And those developments will continue to serve us in future research into cold fusion, but also potentially countless other adjacent fields of inquiry. So while it's safe to say that opinions are still split about this and what kind of outcome this is, even that more negatively slanted futurism piece concedes that there are positives to this outcome, even if we didn't end up with a world-saving, civilization-evolving innovation as we might have hoped. That context established, let's talk a bit about some other facets of this story, including how it overlaps with the worlds of business and technology, but also how it nudges up against our perception of reality. One interesting question here is, why Google? Why did they spend millions of dollars on something as obscure, but also relatively risky in terms of expected outcomes, as cold fusion? That first question is relatively easy to answer, and the second is something about which we can engage in some informed speculation. Google, though primarily known by most people as a provider of search services, web services like Google Docs and Google Drive and Gmail, and perhaps even their hardware like the Google Home, Pixel phones, and Chromebooks, not to mention the Android operating system and Chrome OS that runs on many of those devices. Google is actually a broader-based company than those well-known major moneymakers would imply. Google is actually, as of late 2015, just one sub-company of the umbrella corporation, Alphabet, which was mostly a corporate restructuring for organizational, tax, and expense-related purposes, but this also allowed them to spin several existing projects off into their own businesses, and to recompartmentalize certain efforts into buckets where they make more sense. Thus, an earlier internal project called Google X was renamed X Development, though it kept to its previous specialty, that of a semi-secret R&D setup that works on a variety of moonshot-style efforts, high risk, high investment, high potential reward, that can be funded by other departments within Alphabet, but which can also then inform and play well with those other departments down the line. So X Development is not a company within Alphabet that is meant to make money with its every endeavor, because most of those endeavors will almost certainly fail, or lead to nothing, or lead to less than they might have hoped. But the 1 in 10, or maybe even 1 in 100 that does pay off, will pay off big. Previous X development efforts have included the driverless car and navigation software, Waymo, the balloon-based stratospheric internet project, Loon, the flying delivery vehicle project, Wing, the renewable energy project based on the energy storage potential of molten salt, called Malta, a geothermal technology company called Dandelion, a massive kite-based wind energy company called Makani, and those alongside efforts like Google Glass, the Google Contact Lens, Google Watch, Daydream View, Flux, Chronicle, and Google Brain, which unto itself, because of how it evolved the company's deep learning architecture and understanding, has apparently paid for all of the other X development projects combined. So again, big risk, big reward. Looking at the company through that lens, it's perhaps easier to see why they might look at cold fusion and think, okay, big risk, big reward, this is it. This exemplifies that concept. What that might look like in practice, though, if they actually manage to play a role in discovering a means of achieving reliable benchtop cold fusion, is another matter entirely. It could be that as funders of the research, they would own or partially own or have favored status in regards to certain patents that would allow them to start their own cold fusion-based energy company, to go along with all of the other energy endeavors that they've tried. It could be that they would have a head start in the market, allowing them to leverage their massive resources to jumpstart an energy revolution, even though the patents would technically be available to everyone. Or it could be, and this actually seems somewhat realistic in sociological terms, even if somewhat less so in direct economic terms, it could be that they would just get to claim to be the company that solved all future energy crises, that moved the world away from climate change instigating polluting technologies, that sparked a global renaissance, that increased equality and improved life for essentially everyone on the planet. In terms of soft power, like that wielded by cultures and countries with powerful music and film industries, for instance, or those who have had solid diplomatic reputations internationally, this would be a big move, and perhaps even more profitable in the long term than simply owning a certain patent that would allow them to monetarily benefit for a little while until someone else came up with another method of achieving the same or something similar. There are historical examples of governments swooping in and forcibly taking patent rights and technological know-how from companies like Google, but that's rare. And although it's not outside the realm of possibility that someone somewhere could do this, I imagine China wouldn't feel too bad about hacking Google to get what it needs, and then introducing that technology through one of their homegrown companies, as they've done with other technologies in the past. Though the US government could also decide this technology is of vast strategic importance and thus justify taking it for themselves, it's also likely that if Google made it happen, though, they would benefit greatly in some way, before and after the tech becomes widespread and mainstream. So both risk and reward was high going into this, and though it has nothing to do with search or email, this move was actually squarely within the Google, or rather Alphabet, wheelhouse. Beyond Google's interest in this space, though, is the question of how corporate involvement within the world of public research influences that research. There's not a lot of raw data on this, as it's a tricky thing to measure, and based more on almost vibe reading than number crunching. So keep that in mind and take all of this with a grain of salt. But it does seem that certain types of projects, especially those with immediate relevancy to technological application and to those with future tech potentiality, like in the case of cold fusion, which would spin off into countless other technologies within a few years of becoming a predictable, useful bit of tech, those get a lot more money and a lot more funding than more ephemeral-seeming hard science. Questions about the nature of reality, about neutron stars, about muons and quarks, and so on. This isn't inherently wrong in any way, but it does have a knock-on effect on the world of scientific inquiry because of how it distorts the research scene. If you're a scientist, and all of the funding is in particular fields, these highly productizable fields that companies like Google and Apple and Facebook will be interested in, your incentives are distorted by their presence in that space. Even if Google is not trying to mess with the amount of time and energy and other resources being spent on muons and quarks and anything else, that they are there with money, with the support they can offer over time, that changes things. And because these are highly specialized fields with a finite number of people involved and other resources involved, That a large number of the people and these other resources are applied in these specific directions cannot help but slant the whole research world toward fields and angles that are favored by these well-moneyed corporations. So this isn't an inherently negative or positive thing, it is just a thing. But it's worth remembering that these changes occur when you drop an entity like Google into a space filled with people who are nearly always scrambling for the few available resources to begin with. Google's gravity well is even more intense in these sorts of relatively, and I would argue criminally, underfunded fields. I want to mention briefly once more that the spin-offs of this type of research are often just as, or at times even more, valuable than the thing we intend to discover when we fund research of this kind. I did an episode of the podcast a few years ago where I talked about some of the spin-offs that NASA has developed over the years, a whole catalog of them, and some of the products and technologies that we take for granted today were discovered accidentally or incidentally by them and by companies they hired to do space-related things, because they needed to solve a problem or because they were looking into new stuff and discovered other interesting things along the way. The same is true when companies invest in research, and although the genesis of these things is not always clear or not always a straight line, we often benefit greatly from exploration if we pay attention along the way. Google's contact lenses, initially developed to measure their wearers' blood glucose throughout the day and thought to be a path longer term toward always-on augmented reality lenses, helped Google learn how to put an antenna in a very small and transparent device and how to safely store energy in a flat device that is both tiny and rests on a person's eyeball. Two discoveries that could be worthless dead ends or could be incredibly valuable in some future device. We don't always know right away what these developments will lead to, but some of them eventually become that silver bullet to a problem that would otherwise keep us from moving forward in a nearby or far afield industry or use case, immediately or many years in the future. And finally, I think it's worth addressing here the role that taboo has played in the relative lack of discussion about and research into fields like cold fusion over the past several decades. As a theory, the concept of cold fusion breaks some fundamental rules about how energy works. In short, you shouldn't be able to get more energy out than you put in. This explains, superficially, why so many scientists are hesitant to give this realm of inquiry any of their time or thought. We know it shouldn't work. There's no reason to believe, within the confines of our current understanding of the universe, that it could work. So why even bother? One argument against this way of thinking is that everything should be on the table. The scientific method gives us a way to sort through speculation to arrive at something closer to fact. But if we don't apply that method to a vast expanse of possibilities, we have no idea what we might be leaving on the table and how we might need to reshape our understanding of things over time. And at the end of the day, our scientific understanding of things is always in flux. It changes minutely on a regular basis, and greatly on a semi-regular basis. That's the nature of the beast, but also why it is so powerful and dependable. If we allow any current state of understanding to become dogma, we are setting ourselves up to miss out on some new groundbreaking discovery, some new paradigm shift that we could be experiencing, and relegating ourselves to only ever seeing part of the picture, to understanding some things, but perhaps misunderstanding or looking past just as much or more. Now, the counter-argument to that argument, in the case of cold fusion, is that there could also be invisible unicorns frolicking around us at all times. But because they're invisible, and because we cannot feel them as they pass by, maybe because they're too fast to ever touch, we cannot detect them in the normal way. Now, I could make that claim about the unicorns and demand that we invest scientific resources in checking the veracity of my claim. And the scientific establishment would almost certainly, and rightly, I think, ignore my plea. In order to invest those sorts of resources in terms of equipment, money, and the time of specialists who know how to use that equipment and can spend that money appropriately, it's prudent that we have some reason to think that a particular exploratory path is a good one to walk. Every path we take makes every other possible path into an opportunity cost. And cold fusion, like those unicorns, has shown itself to be fun to think about, but not practical, based on reality as we currently understand reality. That means that we'd be making a lot of other more likely to prove beneficial paths, opportunity costs, to pursue a, from some perspectives at least, unicorn-like flight of fancy. If we discovered a species of unicorns that can blend in with the environment, using some kind of advanced camouflage and which can move so fast that barely anything can touch them, well, that might change things. That could lend credence to the idea that there might be another similar species out there that has gone completely invisible and insubstantial and could lead to some kind of hypothesis that we could then test. The idea would seem more credible and likely to lead us somewhere valuable. And the same is true of cold fusion and similar technologies. As things stand, we do not really have any reason to believe that it's possible. And some would argue that testing it, even with the relative pocket change that Google tossed its way, is a waste of resources that could be better spent elsewhere, could be more productively utilized on ideas that are more firmly rooted in reality, as we understand it today anyway, and thus could have had more beneficial outcomes. Both of these arguments are valid, depending on what you hope to achieve and how broadly you choose to interpret words like utility and possible and reality. Both are also valid depending on which aspect of science you want to be working on and sponsoring at any given moment. It's also worth considering how influential politics and pop culture might have been in this regard in popularizing and ridiculing the concept, making it more appealing and realistic by some standards, while at the same time making it seem less appealing and worthy of study by others. Whatever path we choose in any particular circumstance, with any particular realm of inquiry, it's ideal that we know as specifically as possible what sorts of benefits and insights we want to be looking for along the way, as that can help us set the appropriate tone and expectations when it comes to what a positive or negative outcome looks like at the end of the day. If you're enjoying Let's Know Things, consider taking a moment to leave a quick review wherever you get your podcasts. Now, Apple Podcasts is the OG in this space. The reviews there tend to be disseminated more broadly and thus tend to be more broadly helpful. But wherever you leave a review, there is a chance that somebody at some point will see it and will take that seriously and use it as an excuse to give the podcast a chance. And therefore it makes it more likely that somebody who might enjoy the show might take the time to expose themselves to it. And that is the hope here, to get the show in front of and in the ears of more people who might find it valuable. So when you have a free moment right after listening to this episode, perhaps, leaving a quick review could have an outsized effect. It could be way more impactful and valuable than you might suspect for the time and effort invested. A huge thanks to everybody who has already done so, who's already shared the show with a friend who they think might enjoy it, who's talked about it on social media, who has sent me a lovely email or message or spoken to me at one of my tour stops about how much they're enjoying the show. Thank you so very much. All of that feedback means a whole lot. All of that sharing means a whole lot. And that is the reason that this show is growing and sustaining in the way that it is. And I truly appreciate that. The podcast that I'd like to recommend today is one I started listening to maybe 4 or 5 months ago, and I don't remember where I initially heard about it, but I remember checking to see who the host was, and it's a woman named Rihanna Giddens, and it turns out that she is the lead singer of a band that I really like, the Carolina Chocolate Drops. And as a consequence, I gave this show a listen, in part because of that, and in part because I liked the concept and wanted to know more, and I ended up really enjoying it, and I've gone through almost their entire catalog at this point. Now that said, the show itself, Aria Code, is about opera. It's learning about a particular aria, a part of an opera, in each and every episode. And if you're familiar with the Song Exploder model, it's a little bit like that. Rather than having the writer of these arias come on the show, she has different experts whose expertise lie in elements of theater, of opera, of things related to the song itself in some cases, like gender issues or psychology, depression. And she speaks to these different experts about what the aria means, about what the people in these arias are going through, and about that aria's place within history and other broader contexts. It's really, really lovely. As somebody who knows very, very little about opera, I now know a great deal more than I did before I started listening to this show, but it's also something that I find myself having an increased appreciation for as I learn more about the context in which these arias exist. So just like anything, I suppose, the more you learn about something, the more you can appreciate the implementation of that thing. And now I find myself enjoying any opera music that I listen to all the more because I have that more fundamental understanding of it. Whether you've ever been interested in learning more about opera before, or if it's something totally random, as it was for me, the show Aria Code, A-R-I-A Code, is definitely worth your while. And if you have a chance, if you have something like that, a podcast that you've been listening to that is about a truly random or very niche concept, that then takes you through it and teaches you the fundamentals of that concept, helps you understand in this way, do send that podcast show my way. I would love to indulge in more of these sorts of shows and learn more things about random fields that I currently know very little about. You can find out more about me and my work at colin.io. You can find my blog at exilelifestyle.com, and you can find the show notes for this episode and every episode of the show, along with transcripts of the more recent episodes, at letsknowthings.com. You can find out more about the tour that I'm currently on and where I will be next and get your tickets if applicable at becomingtour.com. And you can find my advice column about life at somethoughtsoboutliving.com. Feel free to reach out and say howdy. I am Colin Wright on Facebook, and at Colin is my name on Twitter and Instagram and YouTube and probably a million other places that I don't go to very often. Thank you so very much for listening. I'm Colin Wright, and I will talk to you again next week.